The natural rivers take different forms and colors that are not seen in man-made concrete channels. It is due to many things such as geometric conditions, flow conditions, vegetation, but most important is the effect of the sediment or the sand and soil in natural rivers. The present topic is about the sediment in rivers, its interaction with the river flow, the vegetation, and other objects in and around rivers. The interaction with vegetation is very important, but not discussed in this topic. These are Google satellite images of two large rivers, Pearl River in Malaysia and Tonegawa River in Japan. Both carry similar normal discharge of about 500 to 1,000 tons per second of water into the ocean. The one in Malaysia looks winding around, and the one in Japan looks more straight. The more distinctive difference, however, is that the Pearl River looks more brown than Tonegawa. The reason is that Pearl River carries much more sediment than Tonegawa. Yes, rivers are the flow of water, but it is not just water that is transported, but other substances are also transported with it. The most common is the sediment, which is part of the river bed, the river materials. Since the sediment is part of the river bed, it changes the shapes of the river or even banks and the surrounding land. In this topic, we will learn how the sediment is removed from the bed, transported along the river, and may also be deposited before reaching the sea. These are the subtopics that will be discussed. 3.1, we discuss the sediment in rivers in general. 3.2, we discuss threshold of sediment motion and its transport. And in 3.3, we discuss movable bed and bed forms. So first, what is sediment? Sediment is part of natural material on Earth's surface, broken down into small pieces and transported by water, wind, or glacier from land higher elevation to the lower land and the sea. Sediment originates from the rocks and has the same composition as the parent rock. They may be classified by a few different ways. One by the composition and the second by the size of the grains. The mechanical properties depend on the specific weight, which is dependent on the composition, and the size and the shape of the individual grains. Since the composition is mostly silicon-based compounds, unless the river carries such things as heavy metals like gold, the specific gravity may be considered fixed around 2.6. The shapes vary, but mostly round, especially after they are eroded as they are transported. So the main difference is the size of the grain. So we classify by the size of the grain. This table shows 4 different kinds of sediment: clay silt, sand, gravel, cobbles, and boulders. The clay and silt go from something like less than 1 micrometer in diameter to like 63 micrometers. Sand goes from 63 micrometers to about 2 millimeters. Gravels are larger than 2 millimeters but smaller than 32 millimeters in diameter. Cobbles are larger than 32 millimeters, and boulders are larger than 256 millimeters in diameter. Most of the time, the sediment consists of different sizes, so one needs to consider the average size and the size distribution. Again, looking at 2 rivers in Malaysia and Japan, a little smaller ones. Sungai Kinta or Kinta River carries small grain, sand, and silt, which are mostly suspended in water, making the brownish color, like on the left-hand picture. Ibogawa River in western Japan, on the right-hand side, consists of larger sediments such as cobbles and boulders. They are less mobile and stay on the bed except during large floods. Now we look at the behavior of sediment particles in water. First, in still water. Since the specific gravity of the sediment particle is larger than 1, they tend to fall in water at rest. The terminal velocity, or the fall velocity, is the velocity of the particle that falls at constant speed under the action of gravity in water at rest. The forces that act on the particles are the gravitational force, mg, and the force water acts, or the resistance, F, on the particle. When the gravitational force and the resistance force of the water are in balance, the velocity becomes constant. This constant velocity is the fall velocity, or the terminal velocity, since it is the final velocity reached as the particle falls from high position. The equation of motion, or the balance of the forces in this case, is expressed by equation 1. F may be split into two parts, Fs and Fd. Fs is the force water exerts on the particle even when the particle is not moving. It is the buoyancy force and is due to the hydrostatic pressure. Fd, on the other hand, is the resistance due to the motion of the particle relative to the water and is called the hydrodynamic force. Now, mg minus Fs is the net weight of the particle in water and is called the weight in water, and denoted by W prime. Then equation 1 may be written like equation 1 prime, and W prime is proportional to the difference of particle density and water density, and the volume of the particle Vs multiplied by the gravitational acceleration g. The hydrodynamic force Fd depends on the speed and the exact shape of the particle and the water viscosity. If we use the drag coefficient Cd to express this force, it is written in this form. As is the largest cross-sectional area of the particle, and Vfs is the fall velocity. So the fall velocity can be obtained by solving this equation too. For perfectly spherical particle, we know that the drag coefficient Cd is a function Reynolds number only. And if the Reynolds number is very small, in such cases as small particles like silt, the exact solution for Cd is available as the Stokes law, and it is given by 24 over Reynolds number based on d. Cd equals 24 over Red. This Red is a Reynolds number based on the diameter d and velocity Vfs. If we use this in equation of motion of particles, equation 2 in the previous slide, the fall velocity Vfs can be solved as equation 3. Note that Vfs is proportional to the square of the diameter d. For large sediment particles, Cd is given graphically. So a trial and error type method may be used to solve for Vfs. For particles that are not spherical, Cd will be a complex function of the shape and the Reynolds number. Since it is not practical to solve for Vfs theoretically for general particle shapes, empirical formulas have been proposed. Most commonly used one is due to Soulsby, which correlates Vfs to the non-dimensional diameter d star defined by this equation. If the equation is too cumbersome to use, a graph like this may be used. Sediment particles do not always fall at this speed in moving water or in water of finite depth. Vfs is more of a property of sediment particle and is used as a parameter in evaluating the motion in moving streams. The sediment particles in moving streams move in different ways. We call the different ways the modes of sediment transport. First, large particles move on bed by rolling, sliding, and hopping, like this. Rolling, sliding, and hopping. This mode of motion is classified as the bed load. The second mode occurs when small particles, which have very small fall velocity and easy to be picked up and moved by the motion of the water. It is called a suspended load. The word sediment load means the amount of transported sediment. We now consider the motion of sediment particles in moving streams flowing on a rigid bed. The equations of motion of solid particle in water without getting in contact with the bed is given by the equation with the gravitational force and the fluid force, or the weight in water and hydrodynamic force, like in equation 4. When the particle is very small, W prime is very small, then the particles move at the same velocity as the fluid, and Fd, which is caused by the relative motion of the particle in water, becomes 0. So the equation becomes like 5. Particles in moving water near the bed now are influenced by additional force from the bed, T. So the equation becomes like 6. At the threshold of motion, the acceleration is 0, and we have the relation that W prime, Fd, and T balance as in equation 7. Now, this is the end of topic 3.1.